search of our cosmic origins. Located high in the Andes mountain range, the 66 antennas that make up the Atacama large millimeter submillimeter array, ALMA, are an imposing sight. Under one sky, more than 20 countries embark upon a scientific endeavor that can only be realized through collaboration. North America, Europe, East Asia, and Chile work together to answer humankind's fundamental questions. Northern Chile was chosen as the site for ALMA because the Atacama Desert is the driest in the world. Its atmosphere, almost devoid of water vapor, enables detection of some of the faintest signals from the universe. Over 16,500 feet above sea level and covering distances of up to 10 miles of the Chajnantor Plateau, the Alma Antennas work as a single large telescope. A supercomputer combines and synchronizes all of their signals in real time. Thanks to this engineering and scientific feat, we're learning about the cold universe, the secrets of planet formation, and the chemical elements that constitute the building blocks of life. Professionals from around the world work for ALMA, pushing the limits of knowledge every day. In Chile, about 50 staff members are based in Santiago, while another 200 work in shifts at the Operations Support Facility close to the town of San Pedro de Atacama. Most of the staff works in the offices, laboratories, and antenna control room of this facility at an altitude of 9,500 feet. Others ascend to the Chajnantor Plateau at 16,500 feet to maintain and relocate the antennas, among other tasks. Strict safety protocols are crucial under these conditions. Thanks to leisure and residential facilities, staff can lead a healthy lifestyle, playing sports and games, watching movies, enjoying nutritious meals, and resting in comfort. ALMA plays a key role in global astronomical efforts. Along with other radio telescopes, it allowed the first image of a black hole to be captured. Without ALMA, that goal would have been unattainable. The Chilean astronomical community actively participates in ALMA research and discoveries, using its 10% of observing time. The radio telescope also contributes to workforce development and supports national and regional scientific, technological, and outreach projects. An example of the latter are the thousands of visitors who tour the facilities each year. ALMA respects the local Licanantay or Atacameño indigenous culture, supporting educational and other projects in the town of Toconao in San Pedro de Atacama, preserving archaeological heritage sites, and protecting the unique flora and fauna of the region, to name a few initiatives. Mirroring the antennas that work in unison with one goal, under the same sky, the international collaboration that ALMA embodies continues the search of our cosmic origins.
Hi everyone, welcome to our virtual tour today. Thank you for joining us. My name is Thais Mandiola. I'm a visitor coordinator at the observatory. Today we will have a great guest again, and in this instance we will go especially about how ALMA generates images, okay, after these observations. But before starting, it's important that we clarified that at this moment, and since a year and a half ago, no visits are being made to the observatory because of the pandemic. And Alma is not 100% operational yet, but our interviewees will let us know a little bit more about how the operations are running and how the observations are running too. Let me tell you a little bit that today we have about 260 people working in Alma, but few know that the 80% of the staff is Chilean and that 65% of our staff work at Alma facilities in the north of Chile, near San Pedro Atacama. Let me introduce you today our guest. We have Laura Gomez, she's an astronomer, and Drew Brisbane, also an astronomer from Alma. Hi, Laura. Hi, Drew. How are you guys?
Hi, Thais.
Thank you for being here today and helping us also to understand better how is the process to make an image with Alma, with the observations. So before we get into subject, it would be interesting that you let us know more about your journey and how it took you to work in Alma, to get to work in Alma. So let's start with you, Laura, if you can tell us what you study, where, and how you got to work here.
Sure. Thank you, Thais, for having us today. Yes, so I studied my bachelor in science in physics. Then I went on to do a master's degree in astronomy and also a PhD in astronomy. The bachelor degree and the master's degree are from Mexico. And I went to Germany for doing a PhD in astronomy. I specialize in the study of the regions where we think that massive stars, which are stars with more than 10 times the mass of the sun, are burning. So, are born. I study the physical and chemical properties of these regions. And then I came to Chile. It was a contract with the University of Chile and an institution in Australia, in Sydney. And after that, I came to Alma, and it is more like 6 years now.
Okay, perfect. What about you, Drew?
Well, first of all, thank you so much for having me, Thais. It's great to be here chatting with you and sharing some of this work with your viewers. So I got my start similar to Laura. I studied physics as a bachelor's degree from my home state of Minnesota in the United States. And from there, I went to Cornell in Ithaca, New York, and got a PhD in astronomy. And that's really where I began my special study of high redshift galaxies. So high redshift, this means that I'm looking at galaxies that are very, very, very far away. And of course, as I'm sure many of the viewers know, light takes a finite time to travel. So this means that if we look very far away at galaxies that are very distant, we're actually looking back in time and getting a picture of how galaxies looked like in the early stages when the universe was still just kind of a baby. And it turns out that these galaxies are a bit different from the galaxies that we see today. They have often very violent or very, very vigorous star formation, I should say. And of course, one way that we investigate these galaxies is by using submillimeter and millimeter waves. And that's really what led me to use ALMA a lot in my own research. That eventually led me to take a postdoctoral position here in Chile at Universidad Diego Portales. And then after that, I began working more and more with ALMA and eventually decided to come and actually work here in the offices in Santiago.
Perfect. And your position in Alma, if you can tell us what it is about, your functions?
So I'll say that I'm a science archive content manager. And this means that part of my duties include looking at data, looking at observations as they come in, and sort of moving those observations from the raw data phase into something that's more like an image that scientists can then take and do their research with.
Okay, perfect. You as well, Laura, no?
Yeah, that's correct.
The same
I'm
position.
a science archive content manager.
Perfect. So about that subject, that to create an image from the observations that has been done in Alma, to just get into context, we will show a short video that will let our viewers know how this process starts. No, so let's watch this. Why astronomers use Alma video about the invisible light.
What if you could only see one color? Not that everything in the world would be the same color, but you could only see things that were, for example, green, and everything else would be invisible. Not such a pleasant reality, is it? Well, it turns out that in a way, it's true. When you look around you, your eyes see what scientists call visible light, and that light, the one we're used to thinking about, is just a very, very small portion of all the different kinds of light that exist in the universe, and most of them are invisible to our eyes. But there are animals that are not blind to those kinds of light. That's why snakes can see even during moonless nights, and bees can see the flowers with the biggest amounts of pollen. They can see lights that we, humans, can't. Snakes can see infrared light, the same kind that allows you to see if you put night vision goggles on. And bees can see ultraviolet, the light that gets your skin burnt unless you protect yourself with sunscreen. All these lights are part of the electromagnetic spectrum, where there are also radio waves, microwaves, X-rays, and gamma rays. All the other lights that we can't see, but are essential to our daily life. Microwaves are used to heat up your food, and X-rays that can go through skin are used by doctors to see your bones. The thing is, the story of the universe, of galaxies, stars, and planets, is told through all of these different kinds of light. And because our eyes are no good to see beyond the visible light, astronomers created new eyes that allow them to see far more, telescopes that can see the invisible light. Alma is one of those telescopes. It can see radio waves. Some places in the universe look dark to our eyes, but shine bright in radio waves. The places where stars are born, for example, are full of dust which blocks visible light, and therefore they are very dark. But radio telescopes like Alma can see straight through that dust. They can see stars being born. They allow the study of things impossible to study otherwise, like galaxies that are very, very far away, or even the birth of other star systems like our own.
Great. So seeing that, we have more of a context of what Alma does, no? So you can help us with your presentation about this process and walk us through on how you generate the images. It will be very interesting to see.
Thank you.
For a lot of people, it's kind of a mystery, so we will uncover.
We hope to explain a bit more. So yes, again, thank you so much for having us. Drew and I will be talking about the creation of images with interferometers like Alma in particular. An interferometer is an array of several antennas that will work together to observe the space, some celestial objects, and from there we will get the images. So, but how does Alma make images? Before answering that question, first we would like to explore these two other common questions. One is, are astronomical images real? The second question is, are they what I will see if I was there? So we will see in a few moments that any kind of telescope use detectors or sensors. So to capture the incoming light. Perhaps when one hears the word telescope, the image that comes to our mind is the usual picture of an optical telescope. So in this case, like the one we see in this slide, the sensor of the telescope can be our own eyes. But we could also attach other types of detectors, so like a camera. And these kind of sensors are also found in our cell phones, for example. So in a sense, yes, these sensors get real images or pictures, but are limited to the type of light that they are able to see. Like we saw in the video that the electromagnetic spectrum is made of several kinds of radiations. So the image that we get depends on both the sensors and the object we view. For example, did you know that the color of the sun is in reality all colors mixed together? From the space to our eyes, it will appear white. So this means that even though the sunlight peaks at the bluish greenish colors, uh, when we capture the light and process that information in our brain, the color will be kind of white or yellowish. But of course, the Earth's atmosphere plays an important role here, because during the sunset and during the sunrise, the sun seems to be of other colors, like red or orange. But that's due to the interaction of the sunlight with the particles in our atmosphere. And that's why we seems to be of other color. Uh, some telescopes have sensors which are similar uh, to our eye sensors. So meaning that they receive the light that we call visual light, and are basically what we would really see if our eyes were that sensible. So in some cases, the telescope use filters, and here in this slide, I'm showing an example of an doubly ionized oxygen filter that it it is manufactured in a way that will capture only the light around 500 nanometers, and this is an important ion that it is found in some objects like planetary nebula or supernova remnants. We saw in the video that our eyes are able to see only a very narrow part of the electromagnetic spectrum. So the part that we see is the visible light, but there are other types of radiation that our eyes cannot see. Like, for example, the radio waves, the microwaves, the infrared, the X-rays, gamma rays. And in order to see other types of light, different kind of telescopes and sensors have been manufactured. And that's the case for Alma. This slide shows a photograph of the Alma Antennas here at the Atacama Desert here in Chile. And those antennas are also telescopes. So the sensors that these antennas use are located in the back of each antenna. And in that container, which is called the cryosat, it has several detectors. In this case, I'm showing the picture for a detector of the band 1 receiver. And in the next slide, it is another picture from a very similar detector of receiver, but this is for another band. This is the band 10 receiver. And so in this case, this detector receives light or frequencies from 787 gigahertz to 950 gigahertz. There are other detectors in the cabin of the antenna, and they can cover, for example, from 92 to 108 gigahertz. Other detector receive lights from 211 and 275 gigahertz, and so on.
So Laura,
Yep.
could you give us a little, like an example of which can be able to observe depending on these frequencies?
Yes, so depending on the frequency, we can observe, for example, different types of molecules. There are some molecules in the that can the type of movements of their molecule radiates at certain frequency. So not at any frequency, they are fixed frequencies, and that's why the receivers are manufactured so that we can receive, for example, light from those, like the frequency from those.
Okay.
So that's one of the advantages of have several spectral windows to have several molecules, for example.
Thank you.
And so beginning with finishing this part with the first question we have, how does Alma make images? So the first question we had, are astronomical images real? Yes, at least as real our image of white yellowish sun. Are they what I will see if I was there? Not necessarily, because with some telescope, yes, like the optical telescope that can receive light um, similarly that our sensors, our eyes can receive. But there are other wavelengths or frequencies that our eyes cannot detect. So those I wouldn't have the ability to see them because my eyes cannot. We are limited in that sense. And this is an example in which there is the same galaxy but that was observed in different wavelengths using different telescopes, using different detectors. Some telescopes are ground-based, like for example, in this case, which is observed with visible light in La Silla here in Chile. Ground-based also is Alma. The observations are focused mainly in the central part of the galaxy. This is also ground-based, the VLA. It is a radio interferometer located in the United States. There are also there are telescopes in satellites like the Spitzer satellite, the X-ray Chandra. And as you can see, even though it is the same galaxy, it looks very different depending on the telescope that the scientists use. So the information we get from those observations is complementary and helps astronomers to better explain what's going on for a given celestial object. Um, so I'm finishing the first part here, and let Drew continue.
Okay, thanks, Laura. So I'll start sharing my screen over here. And here we go. So that was a really great, way to learn about some of the basics of making images in astronomy in general. But of course, we're here to talk about ALMA specifically, and ALMA is a little bit special. As you know, ALMA is an interferometer, and interferometers work by detecting directly, rather than detecting the image directly, they measure the spatial frequencies in a field of view. Now this, this can be a very technical, mathematical topic. They're able to do this because of the wave nature of light, and also the ability to directly record the phase of a light wave. So that is the ability to measure those peaks and troughs and where the light is currently in those peaks and troughs of a light wave. So we can get very deep into this, but really all of that technical discussion would fill up many talks, which we don't have time for right now. So I'll just say that if this is something you're interested in, there are lots of resources available to learn more about this. You can start with ALMA's own website here that I put the link to. If you're looking for, there's also plenty of YouTube videos available that are very rich resources for this. Or if you want a more advanced or technical description, there's several great textbooks about this. I've just listed one of them, Interferometry and Synthesis in Radio Astronomy, which of course you can try and find a copy of and check out for yourself if you're interested. But right now, let's try and get a kind of a gut feeling, an intuitive feeling of what goes on here. And let's start by talking about these spatial frequencies that I mentioned. So what do I mean when I say spatial frequencies? Well, to take an example, I'd like to show you an image here. This image is it's not actually of the center of the universe, but it is an image of something that kind of thinks it's the center of the universe. This is my own lovely cat, Serpentina. And here I have a picture of her on the left side. And if I want to examine the spatial frequencies in this picture, I can do that by using a mathematical tool called a Fourier Transform. Basically, this is a mathematical tool we use. We can feed in a two-dimensional image, and it will spit out something like what looks like this image on the right here, which is actually giving us a power spectrum of all the different spatial frequencies in this initial image. By the way, you'll often hear me referring to this kind of an image as the Fourier Domain. And a bit later, you might hear me referring to this particular pattern here as a visibility, and we'll see why in a moment. But the things to take notice of here are that this gives us all of the same information that's in this picture. It's just presented in a different way. And what we have here is actually every single pixel on this image on the right gives us one spatial frequency in X and Y of this picture. And in particular, all of the low spatial frequencies, these low spatial frequencies correspond to patterns in this image on the left, which are very slow moving. They vary slowly across the image, both up and down and left and right. And those low frequency images are all located near the center of this Fourier domain. Out on the outskirts, the edges of this image, this Fourier domain, those are the high spatial frequencies. And those high spatial frequencies correspond to the details in this image, the high resolution pixel to pixel variation that occurs at a very small, in a very small spatial scale in this image. So to get more of an intuitive sense of what this means, we can actually do some kind of rudimentary image processing using this Fourier domain. For instance, let's say I've got this picture of my cat Serpentina, and I want to just pull out and just look at those low frequency, the large scale patterns in this image. So one way I could do this, I could take the image, transform it into the Fourier domain here, and then apply a filter to it, which I will call a low pass filter. Basically, this white dot in the center is going to save all the frequencies in the center of this Fourier domain. Remember, those are the low spatial frequencies, and everything around it will be thrown out. We'll ignore all of these high spatial frequencies on the outskirts. The result, when we multiply this filter by this visibility, is a sampled visibility, like this one on the right here. And if I now transform that back into an image using an inverse Fourier transform, I get an image that looks like the one up here on the right. So now you can see that all of the very high resolution detail in the image has been washed out, and we get a much blurrier photo. And of course, we can do the reverse of this as well. Say if I want to really pull out those high detail information, the edges that we see in the image, I could do this by inserting a high pass filter. So now I'm just going to throw out all of those frequencies in the center of the Fourier domain, the low spatial frequencies, save all of the high spatial frequencies. I get a new sampled visibility over here on the right, and I can inverse Fourier transform that into an image. And now you see the image really is just an image of those edges. We really see the very, very fine details and none of that large scale structure in the resulting image. And in fact, you can really play around with this a lot if you want to. You can actually try and focus in on certain special details in the image and try and do things with those details. So in this case, for instance, you'll notice that, there are all of these diagonal lines behind Serpentina, and that's because, of course, Serpentina is a bit of a clumsy cat, and I need a screen on my balcony, or else she would fall right off the edge. But those diagonal lines, maybe I don't want those in the picture. And it turns out if I look in the Fourier transform of this image, you can see that there are these diagonal spikes in both directions here. And those diagonal spikes, I bet, correspond to these the lines that we see in the image coming from the screen. So if I wanted to, I could try and filter those out somehow. So as a very quick demonstration, I tried to do this. I created this filter. And you'll notice that these black bars here, those are trying to cover up these, or filter out these diagonal spikes that I see in the original visibility. So now when I multiply the filter times my original visibility, I get a new sampled visibility, and I can transform that back into an image. And you can see it kind of worked. I didn't do such a great job, but if you look at the sky here, those screen lines that you see in the original image kind of seem to have disappeared, or at least softened up a little bit. But obviously it's not perfect. For instance, Serpentina's little ear here has the same diagonal angle as the screen. So you get a weird artifact coming in there because I've messed up with those spatial frequencies. So it's just kind of a fun thing you can play around with, although if you really want to do a great job, it would take much more time than this simple filter that I've created here. But what does all this have to do with Alma? Well, one of the important things to take away is that even after I've thrown out a huge amount of this spatial frequency information, we still have data that provides an intelligible image. We can still look at any of these images, and even though we've thrown out huge quantities of information, you can still kind of tell that, okay, in each one of these images, there's a cat, there's some mountains in the background, there's a church in the background. You get a general sense of what's actually there. So taking this back to Alma itself again, the way we actually make an interferometer or use an interferometer is by building up baselines, building up pairs of antennas. Each pair of antenna makes one baseline, and each baseline samples one point in the Fourier domain. It samples one spatial frequency, which we can use to detect what's out there in space. So to get an example of this, let's actually kind of simulate building up an interferometer antenna by antenna. So here in the upper left plot, we see a plot just giving us the positions of two antennas. We'll start with the most basic interferometer possible, which includes two antennas. Those two antennas give us one baseline. And if I take this, the actual antenna position, and put it into the Fourier domain, that's the plot right down here, this gives us our sampling function. So these 2 points tell us which spatial frequencies our one baseline will sample in the Fourier domain. And actually, let me step back and note one thing really quick here, a technical detail. You may have noticed I mentioned that one baseline should sample one spatial frequency, but in this plot, there's actually 2 different points here. So that might seem a little bit weird. It seems like we're actually sampling 2 different spatial frequencies. But actually, if you look very closely at this plot, you'll notice that the 2 spatial frequencies are actually mirrored across the X and Y axes. So in this case, even though it's kind of 2 spatial frequencies, they are negatives of each other. And so you're actually not getting any new information from the secondary point. So if I now take this, this sampling function in Fourier domain and inverse Fourier transform it into the image domain again, this gives us a fringe pattern, or we might call this the PSF, the point spread function. The point spread function is a term that gets used a lot for sort of traditional single dish telescopes rather than interferometers, and it basically tells us what the shape of the telescope beam is on the sky. So perhaps if you have a really nice single dish telescope, your PSF will be just a single circular blob in the middle here. Whoops, didn't mean to go that far. It'll be a single circular blob in the center of the right-hand image there. But in this case, we have 2 antennas working as an interferometer. So instead, what we get is this weird stripy pattern. And what this means is that if we were to actually try and use this 2 antenna interferometer, it would provide us some information, but it would be very confusing, because if we were to detect a very bright object in the sky, rather than seeing a nice singular point with our nice circular beam, we would actually see stripes like this. We would see very long stripes in one direction, and then on top of that, those stripes would be repeated in a pattern over and over again in the opposite direction. So if we were to actually try and detect something with this, we wouldn't know if the resulting, the source that we detect is actually in the center of the image, or maybe if it's coming from the upper right-hand corner, or maybe the lower left-hand corner. We wouldn't really have any good idea. So we need to build our interferometer bigger. Let's add a 3rd baseline, or a 3rd antenna. That gives us 3 baselines now. And you can see our new PSF. It looks a little bit different. Maybe it's better, but it's still very stripy, very, very confusing to look at. But we can add another antenna. So now we have 4 antennas, which gives us 6 baselines. Now we still have something very confusing. We have many repeated blobs in our PSF. But let's go to 8 antennas. And you'll notice that now we have 28 baselines. So it's important to remember that every antenna we add adds many more baselines. And now we start to see things that get a little bit better. We actually see a kind of a nice looking blob, a bright blob in the center of our PSF, and some other junk around it. Let's add some more. Here's 16 antennas. So now we're actually getting a pretty good looking PSF. We've actually got a very bright blob in the center, still a little bit of fluffy junk around the outsides. And then the other important thing to note is, remember that I said in the Fourier domain, those low spatial frequencies lie near the center of that domain. So in this case, we've got all 16 antennas clustered in a relatively compact configuration. They're relatively close together. So that means that we're actually sampling these lower spatial frequencies more in this case. So that gives us a relatively big blob. In other words, the resolution on this interferometer would not be super high. It would still be kind of blurry. But of course, here at Alma, we can control how those antennas are distributed. We can make them very compact, or we can extend them into very large baselines. And when we do that, as in this slide, you see that we've spread all of the antennas out. We're sampling a much larger region of Fourier space, including many high spatial frequencies. And indeed, now our PSF gets a bit smaller. This central blob has become much smaller, giving us a higher resolution. On top of that, though, you will notice that there's a trade-off here. We now have really quite a lot of junk in our PSF out here. And, that can be confusing to look at. And the reason for that, of course, is because we're not sampling all of the Fourier domain. There's all of these white spots in between our antennas down here. So that leads to artifacts. But we can keep going a little bit. We can add some more antennas. Here's 32 antennas. And in fact, we can even do a little bit better because this is what's called an instantaneous picture. So if we take a quick snapshot with these 32 antennas, this is the space that we sample in the Fourier domain in the lower left there. And if we are looking at an object for a long time, remember that the Earth is rotating, of course. And what this means is that those baselines, from the point of view of the astronomical source that we're looking at, those baselines will also rotate. So in fact, if we stare at an object for a long time, each one of those individual points in the PSF will become stretched out into a line, sampling a larger portion of the Fourier domain. And correspondingly, we get a better looking PSF. You can see as I flip between these two, that central blob gets a little bit brighter and all of that junk on the outside goes down a little bit. And I should also mention, this is kind of where this building the interferometer demonstration ends, but of course, Alma is even better than what we've shown here. This is only 32 antennas, and Alma actually has 54 antennas that are the same size, and then if we include other antennas as well, it has up to 66 antennas. So what all this can tell us is that even though it works in a little bit of a funny way, it's pretty analogous to the way any telescope works. Rather than directly measuring the sky intensity, we directly measure the visibility, which is the Fourier domain. And rather than sampling it with the PSF, we use a sampling function in the Fourier domain. And this results in a sampled visibility on the right lower corner there, which we can then transform back into an image. So that's sort of the step zero of understanding how to get images with interferometers. But you'll notice that this image that we get isn't perfect. It may give us a good idea of the underlying sky image, but since we haven't sampled all of the Fourier domain, we've actually lost a lot of spatial frequencies, and the image may still have significant artifacts in it. So to improve it a little bit, we can kind of clean that image up. And I have clean in quotation marks there because actually clean is a famous computer algorithm which is used for exactly this purpose. So this is where the software comes into play. And for this software, we use a software application called CASA, the Common Astronomy Software Applications. This is a special bit of software that was developed specifically for interferometry data. And it's publicly available. Anyone can go and download it from the NRAO website. And it's not the only bit of software that can do this. There are other different applications that can do similar things for interferometric data, but this is the piece of software that Laura and I use on a day-to-day basis. So just to see a quick example of how we actually go about using the software, I'll show you one example here. So here we have, this is sort of the initial image that we might get out of these visibilities, which we've transformed. This is what we often refer to as a dirty image, although HR made us promise not to make any jokes about looking at dirty images at work. But you'll notice that it looks a little funny. There's a lot of blobs here, and it's not a perfect, pristine-looking astronomical image, but it does give us some information. Right away, when I look at this, I can see that there are two very bright peaks there, and there's also a secondary elongated blob. So what I might do is I might say, okay, those two peaks, they look very bright. I think those are, that's real emission from the sky. So I'm going to save those two peaks as part of a model image. So we create this whole new model image. We put in those two brightest peaks that we found, but actually we want to do it kind of slowly, kind of gradually, because if you try and do this cleaning process very fast or very suddenly, it can make the whole thing go a bit crazy and you get a whole bunch of errors, which we don't want. So rather than include the full value of those two bright peaks that we saw, we will only include a fraction of the brightness in those two peaks for the moment. So now we have a model, we have this initial image, and we can actually take that model and subtract it from the initial dirty image, giving us a residual image. So if you look very closely, you can see that between the initial image and the residual image, those two peaks have decreased a little bit, and some of the noisy stuff around it has also gotten a little bit smoother. So now we have a leftover residual, we have a very basic model, and we can put those together. We just add the residual image plus the model image after we convolve it with a restoring Gaussian beam to create an interim image. It's called I put final product in this, but that's a bit of a misleading title. It's not the final product. This is just the interim image that we use for the time being, because now we see in our residual image that there's still lots of peaks left there. And remember that every time we subtract the model from the residual, that residual should go down a little bit. So since there's still a lot of messy stuff left in that residual, that means there's still emission components that we haven't modeled successfully. And also, just to give you an idea of what this looks like, I should mention that the top left image there uses a log color scale. That gives us an opportunity to see both very small differences and also very large differences. The bottom left image gives us a linear color scale, which shows us a different format or a different way of looking at those differences. So now we have our next residual image, and we look at the next brightest peaks, the next brightest points in that image, and we include those in our new model. So it's a bit harder to see this difference, but again, flipping between these two slides, you can see that those two peaks have gone down a little bit more because we've now included more of their flux, more of their brightness in our model image. So this gives us a chance to come up with a updated, cleaned image in the lower right. And then we repeat the process. We look at the newest residual. We look for the next brightest set of peaks, which now at this point, we're going to start including that kind of elongated blob in the upper right corner. So you'll see that appears in our new model in the upper right plot. And we just iterate. We subtract that model again and come up with a new residual, come up with a new cleaned image. And we proceed step by step, doing this over and over again. And you'll notice that the residual image becomes smoother and smoother. As well, our model gets updated over and over again, and those emission blobs get bigger and bigger, until eventually we get to a point where we have subtracted everything, essentially everything that's real, and our residual image no longer shows us any real sky emission. It's just some slow, noisy stuff going on there. And once we get to that point, we're left with our final cleaned image. And it's also important to note that this process, as you can see, it takes many, many iterations, many, many steps. In this case, we went through 1,500 iterations. That process is not always, sometimes we do that by hand. Sometimes we go step by step and click our mouse button and draw these circles around the sources that we see and do this manually. But if it's a simple image, if it maybe just has a single detected object in the center, then it's simple enough that we have automated code which is able to do this pretty fast and able to do this automatically.
Drew,
and
one question.
Yes.
So
please.
How long does it take to produce something like that? You said it's faster with this software, but could you give us an example of how long would it take?
Well, it varies a lot depending on how complicated the image is, actually. We have very powerful computers here, and when it's able to be done in an automated fashion, it takes it can take an hour, it can take a few hours. If it's very complicated, it can take many hours. But yeah, if we do it by hand, it takes longer.
And in the case that you shown the last images with colors, could you tell us how do you deliver the colors for this object?
Yeah. So when we work with this, our primary goal is to look at this one image, just this one Alma frequency or this one Alma wavelength, and try and get the best image possible. So when we're actually looking at the computer screen like this, we will use kind of funny colors, like the colors that you're seeing on the screen now. Those colors that we're using while we're processing it don't have any bearing, don't relate to what actual frequencies or what actual wavelengths we are observing. So that's why you get this very rainbow effect when you're looking at these kind of raw images. Now, once we deliver that data to the scientists, they can do what they want with it. Very often, they will take an Alma image and they'll combine it with, say, a Hubble image or maybe a JWST image in the near future. So they'll try and combine Alma images with other wavelengths. When they do that, very often they will like to use, say, for the Hubble image, they use the real visible light, the real visible colors coming from that image. And then if they want to overlay the Alma data on top, so they can compare what shows up in the visible with what shows up in the Alma millimeter regime, then they might change those colors to be not this crazy rainbow effect, but to instead be maybe red, because of course, red is a longer wavelength, and the waves that we're looking at in the millimeter and submillimeter are even longer still. So the wavelengths that we look at are redder than red, if you will. So that's kind of left up to the scientists that use the image.
Perfect. And are there any observations that cannot be converted into images?
In what we deal with, that's not really the case. There is something called time domain astronomy, and actually we do deal with that occasionally. So time domain astronomy looks for changes over time. Of course, a lot of stuff in the sky doesn't change at all. It takes eons, billions and billions of years to change it all. But occasionally there are things that change fast. Maybe you detect a comet, or maybe you have a supernova that is about to go off or has just gone off. And of course, that changes over time. So when you have some data like that, you probably need something to show it off more than just a single two-dimensional image. You might want a series of images, or you might want to take the important data point, say the brightness of that supernova, and plot that brightness as a line and see how it changes over time. But for the most part, most of the data that we deal with Alma works quite well as an image.
Okay, perfect. Thank you. Do you have
My
more
pleasure.
from your presentation that you want?
No, actually, this is sort of the end of the introduction to the journey of an image with Alma.
Yeah, amazing. Thank you so much. It was very clear and very complex, I would say. So we have some comments from Brazil. They're saying hello from Brazil. They're watching us. And we have a user from LinkedIn saying thank you again. This is very interesting topic for myself. There we have it. And we have French comment too that I don't speak French, so maybe Nicolas could help us with that one from Marcel. Is there any other questions, Nico, that are getting into? We have a few more minutes. Not for now. So in the case of the black hole image, if you could tell us how difficult what was that process. Maybe you heard about how it was, or you were involved. If you can tell us a little bit of that.
I bet Laura can tell us a bit more than I can about that.
Yeah, it would be interesting to say because it was a long time.
Well, in the case of the imaging of the black hole, it is using the method of interferometer, but in that case, it used different telescopes around the world, including the radio telescope Alma. And yeah, the challenges are uh, bigger because in that case, you need to coordinate all the other telescopes and in all the other parts of the world, and then you need to combine all the data received from each and every one of the telescope to get the images. So in principle, the methods are more or less the same, but yes, in fact, they have their big challenges to get to the point to present the image.
Were you involved in that process, any of you?
No, I wasn't.
No?
So no.
Well, for the next
Nope,
one,
not
maybe.
me.
And what is coming for the challenges of Alma in the case of what you work in? Can you tell us a little bit of what is coming from the future for the future?
I can tell from at least from the point of view of the star formation area, the line of investigation. At least Alma it's very important because as we saw in the short video about what Alma can see through the dusty clouds in our galaxy, for example. So if I were to use an optical telescope, we will just see a dark blob, but using ALMA, it can go through the clouds and observe what is going on inside. So in that sense, like looking deeper also helps a lot to distinguish between, for example, in my case, if I want to know if a star is burning there,
Mhm.
um, so I would like to see, is it one blob, is it two blobs, is it three blobs? So um,
So
if
more
like
detail.
yeah, so more detail and deeper, so we can see the weakest part of that type of blocks.
Mhm.
And I think just to add on to that, uh, as the video we saw in the very beginning asked, what if you can only see in one color? Every time that we add a new telescope, that we add a new type of observatory to the astronomer's tool belt, that provides a whole new world to explore. But we don't just explore it by itself. Now, for instance, when JWST comes online, of course, we'll be seeing a whole set of new colors from that, and that'll be interesting in its own right. But when we combine, it's really the multi-wavelength approach that lets us see the entire spectrum and really lets us see what's actually physically going on in space. So I think that's really one of the cool things about astronomy, because as soon as the new telescope comes online, as soon as JWST is up, that's not just exciting for infrared astronomers, that's exciting for us as well, because it's really when you combine all of this information together that you get a better sense of what's actually going on.
Great. And for the case of Alma, we have the band one that is integrated. So that will be another opening for you guys, no? For observation.
Exactly.
Mhm.
Yeah, that's true.
Well, Laura and Drew, thank you so much for this amazing presentation you did. I hope that our viewers enjoyed too and learned a lot as well as us. And we'll be finishing now. So thank you very much and goodbye.
Thank you
Thank
so
you,
much.
Thais. Bye.
Bye.